Hey everyone, this is a look through my spatial audio demo in Unreal Engine 5 using material-dependent obstruction system and a room and portal sound propagation system. Here's how it sounds. So for a brief overview of what's going on, you can hear sounds are filtered in different ways depending on if and what objects are between the listener and sound emitter. Also, when the listener is in a different room from the sound emitter, sounds seem to pass through the position of the doorways, which I'll call portals. So the music is coming from that blue box there. And it sounds like it's coming from the position of this doorway. It'll be particularly noticeable if I go near the doorway here. It sounds like it's coming super from the left, even though the box is pretty much right in front of me. Lastly, sounds will be sent through different reverbs depending on what room they are in, and sounds passing through portals will use both their own room's reverb as well as the reverb on the connecting room. So this is a big room, so it has a big reverb, and you can hear that on the music. Sounds a lot drier in here. I come back out. You can hear it's using both reverbs at the same time. So let's take a look at how this is all set up. I'll start with taking a look at the obstruction system. This system filters sounds differently depending on the number of obstructing objects, the materials of these objects, and how entirely they obstruct the emitter. So you can hear how as I walk behind this wooden wall, the sound gradually gets filtered. It's not either all or nothing. There's a gradual component to that. And then the filtering behind the wooden wall is going to be less than behind this heavier rock wall. And then different combinations of walls will also give different results. So if I look at this sort of like synthetic, I'm going to call this drywall, which won't obstruct very much. If I go behind the wood and then also go behind this second wall, the filtering gets low passed even more. So you get a stronger effect behind two walls. Okay, so this whole audio system is using this spatial emitter scene component. This spatial emitter scene component handles all of the spatial audio calculations and things like that, which will drive the MetaSound later on. This spatial audio component can just be dropped right onto an actor as long as it has an audio component on the actor as well. So in this case, we have this orb, and we have the orb audio as well as this spatial emitter component here. So if we hop over into the spatial emitter itself, we can see how this is all set up. So on event begin play, we're going to grab and save the owner, the parent. So this is the actor that the spatial emitter is on. And then I'm going to grab the player character and save that as player. Then I'm going to go into this get audio components function. So we have this multiple audio bool. This is a public bool. This is if you want to have multiple audio components on a single actor for whatever reason, you need a spatial emitter per audio component. If it's true, the way I'm handling this is I'm just having like a matching tag. So you'll need to have a tag on the spatial emitter scene component and a tag on the audio component. It's going to compare those tags and assign an audio component that way. So if there's like multiple of the same tag or there's like no matching tag, I'll throw this error. For now, I'm just going to do one audio component per actor. So it's just simple as this, get the audio component and save it as audio. So going back into the event begin play, I'm going to make sure that the audio component is valid. If it's not, I'll throw this error. If it is, we'll do this get attenuation settings function, which this will be useful for later on. I'm going to grab the attenuation settings right off the audio component. So this is just whatever attenuation settings you put onto the audio component. It returns this attenuation settings struct. I'll break this struct and grab 3 values, the attenuation function enum. So this is like, this is the model that the attenuation uses to attenuate the sound across distance. So it could be linear, it could be logarithmic. There's a few other options. Then I'm going to grab the attenuation shape extents. This is different depending on which attenuation shape you're using. But for like standard ones, like a cube or a sphere, this pretty much will be able to give us a good value for the attenuation minimum. So the minimum distance for when the minimum distance the player has to be away from the emitter for the sound to start getting attenuated across distance. And then I grab this fall off distance, and assign it to attenuation max. So this is the distance from the attenuation min that the sound is fully attenuated, so you don't hear anything at all. So going back up into here, after that, I'm going to set initialized, which is going to set some stuff off in tick. I'm going to ignore this stuff for now, but I'll show it later when we get into rooms and portals. So if we're initialized, then we can start doing all of this stuff. First thing I'm going to do is get and save the parent location, so the location of the actor that this component is on. And then I'm going to get and save the player location as well. Get the distance between them, save that as distance. And then what I'm going to do is add up the attenuation max distance and attenuation min distance to get the full distance away from the emitter itself that you need to be to not hear the sound at all. And I'm going to use that to check if the player is within range of the emitter. So are we hearing it at all? I basically don't want to do a bunch of this stuff if you can't even hear the sound anyways. So I'm going to skip over this collision stuff for now. This is for the portals. I'll get into that later. Really quickly, I'm just going to make sure that the sound emitter is in the same room as the player, or at least the player has entered a portal. I'll get into why later. And then now we're going to get into this get obstruction percentage function. So this takes a target actor, which it will be the player, and a number of obstruction line traces. This is just a public integer. So the way this works is it's going to send a number of line traces from the emitter to the target. And the different line traces will also be positioned differently around the emitter. So this is to give us sort of the feeling of diffraction around a sound. So you're not just getting full obstruction just because something has obstructed your direct view to an emitter. It's also checking positions around the emitter as well to give that feeling of sound going around an object. So let's hop into that function. So the first thing I'm doing here is resetting the working obstruction to 0. So this is a value that's going to be added onto, manipulated, various different things, and then eventually will be outputted as the obstruction percentage. So I'm just resetting this every time this function is called, adding it all up, and then outputting it at the end. Then on this for loop, we're going to just do for every line trace. I have to do -1 because it's based on index. So the first index is going to be 0, or else like the first line trace. So now let's take a look at the set obstruction per line. So this will let us know how much obstruction to apply per line trace. So we'll hop into here. Quickly, we just get the actor location of the target. If we're using the player, we sort of already have this, but as we'll see later, we're not always using the player as the target for this. We'll use that location to then set as the end of our multi-line trace for objects. I'm using the multi-line trace for objects node because a multi-line trace will be able to return multiple hits per line trace. This allows us to have multiple objects obstructing a single line, and we can add all those objects up. It affects things differently, kind of like what I showed earlier with the drywall and the wood wall both obstructing. Then we'll take the emitter location and then find the look at rotation from the parent to the target. So what's going on here is what I'm going to do is set different line traces starting from different positions around the emitter based on this line trace positions array of vectors. We can take a look at that here. Let me just bring this back. We can take a look at that here quickly. Here it is. So like 100 is going to be 100 units to the right. Negative 100 is 100 units to the left. 200, negative 200. Same idea. Those are our different positions through which we will shoot a line trace off. The reason that we need this look at rotation is because I don't want these positions to just be relative to the emitter actor. I want them to be relative to the player. So they're all shooting at you from like the correct rotation. I get the right vector and multiply that by the line trace positions. Because I'm using the right vector, that's why it's going right or left around the emitter, which we'll see in a second. Then I'm going to add that to the parent location. So it's these line traces will start around the parent. After that, we're going to hop over here and set this line working obstruction. So this is pretty much the same idea as that working obstruction from earlier. This is just per line. So we'll be handling this per line. So we'll do a for each loop on all of our hits, as in every object that the line hits. We'll set our obstruction material multiplier to the default, which in this case is 3. So really quick, how the obstruction material multiplier works and what it's doing is there are different values assigned to different types of walls. And that's all set up with tags. So like a wood wall would be tagged with wood, like concrete wall would be tagged with concrete. Let's take a look at the data table, which has our obstruction material multipliers on it. So the way it works is the obstruction multiplier is the amount of obstructors you need for the sound to be fully obstructed. So there needs to be 5 drywall walls in between the emitter and listener for the emitter to be fully obstructed, 4 for wood, 2 for concrete. So a smaller number means it has heavier obstruction per wall. This is a data table. The struct is just this, it's just a float, this obstruction multiplier float. But I'm using a data table so I can compare it against the rows. So back into here. This default thing is basically just so if we don't get any results back from checking the tags of the hit result, we'll still have a default value to go off of. And the default value is 3, which I just felt was kind of in between the various different types of walls. So if we do find some tags, which we do if it's set up correctly, we will then check each tag against the data table. If we find something, we're going to break out that struct on the data table row and then grab the obstruction material multiplier value, set the new obstruction material multiplier, and then break this for each loop. We will just use the very first tag that matches a data table row that we find. No need to continue looking through everything after that. So then I'm going to divide 1 by the obstruction material multiplier. And then add that to the line working obstruction. So like I said before, because it's like you need 5 walls to be fully obstructed, 1 divided by 5, you get, so that'd be like if there's 5.2s, then you get a full 1, so it's fully obstructed. Then we'll set the line working obstruction, which is the total obstruction for this line. After the for each loop on the hits is finished up, we're going to go over here, compare our final line working obstruction for all of our added up hits, and throw it against this obstruction curve. This is just a curve that I manually created. It's just a curve that I felt worked for like the filtering done in obstruction. Then I'm going to subtract this from 1. The reason I'm doing this is because the obstruction value will eventually be linearly mapped against cutoff frequency on a low pass filter. So a higher value would be like less cutoff, and a lower value would be a lower cutoff or more strongly filtered. So back into here. After we get this obstruction per line, we're going to add that to the working obstruction and then set the working obstruction. So then after all of our obstructions per line are finished, and our working obstruction is pretty much all of the different obstructions per line added up all together, I'm then going to divide the working obstruction by the amount of obstruction lines, line traces that we threw out there to get the average obstruction. And then finally, I'm going to send that value to the audio component, which will have a MetaSound on it and a corresponding input for obstruction percentage. So we can just look at that right now. I'll open this guy. So this is the orb loop MetaSound, which was the one that was on that orb that we looked at earlier. This is a pretty simple MetaSound. Over here, it just has an LFO on modulating pitch. As you get closer to the object, the frequency increases and the width of the LFO also increases. This number is being fed by a blueprint on the actor itself. It's also feeding some like particle effect stuff as well, which you'll see when I show it in a second. So the output is taken out of this wave player and then thrown into this beefy patch here, the emitter spatializer. Don't worry about any of this stuff, any of this portal stuff for now. We just want this obstruction percentage, which is the value we just set. So if we head into this patch will handle a lot of the DSP associated with spatialization. So we go into here, don't worry about this portal amount. Let's just assume it's set to 0. We're in the same room as the emitter. And we'll just run all the way up to here and get the direct obstruction. So that's the direct obstruction right from the emitter to the player. We have our input here, and we're going to map that against log frequency. So we can feed this bi-quad filter with actual frequencies for the cutoff frequency. Just have a little interpolation there so it eases a little better. And then a similar thing, I'm going to map the obstruction percentage against this range, 0.1 to 1, so I can lower the gain as well as it gets obstructed. So the sound will get quieter as it gets obstructed. So that is that. Let's see how this sounds in the end. I turned on the visibility on the line traces so we can see what they look like. So as you can see, we have 5 line traces coming from different positions around the emitter. This middle one is coming directly from the emitter, and the other ones are coming from around it. You can see how they're kind of rotating with me. So they're not stuck in a spot relative to the emitter. They are moving freely relative to where I am. And you can see how each one will return a hit as I go behind this wall. Now it's fully obstructed. So you get this nice sort of natural and gradual filtering as you move behind these objects. And it kind of gives that feeling of diffraction, or things moving around an object. So, or sound moving around an object rather. This like red line sort of would be the sound moving around the object. And then you can see it's also can do multiple hits. So it's hitting there and then getting hits again from this second wall. So this would be like 10 hits, 5 on the first wall and 5 on the second. You get extra obstruction. All right, great. So let's move on to the room and portal system.